tiny boards.
Yes. This was our attempt to not force everyone to walk up and get rained on before coming down again. Good. So one very quick announcement. In the interest of truly sort of interweaving, Dima and I will be switching the order of our lectures tomorrow. So Dima will be lecturing first and I will be lecturing second. Please come to Dima's lectures and ask him lots of questions, because I'll be building off of some of the things he explains in terms of flow K physics when I talk about time crystals. Good, so, and today, much of what I'll focus on today is really, in some sense, can be viewed as a complementary piece to Dima's really beautiful introduction. So, in particular, the beginning, which is really kind of the part that has maybe the most overlap, we'll actually try to answer 3 questions sort of complementary to the approach that Dima gave. The first one was actually asked by one of your fellow classmates. What exactly does it mean to be non-interacting? So people talk about Anderson localization and say, well, Anderson localization is a form of localization which is non-interacting, and then we add in interactions and all hell breaks loose. What exactly was the nature of this non-interacting physics? I'll try to give some intuition for the reason why interactions are important and why finite energy densities are really important for thinking about how interactions, in particular the coordinate terms that Dima wrote up today, end up leading to delocalization. And then I'll give maybe a very operational perspective, kind of classic example on the numeric side for how people diagnose this many-body localization transition. So Dima wrote up a beautiful slide at the very end that had the difference between sort of ETH phases and MBL phases, and I'll give a sort of specific example in the numerical context, something that you maybe have heard of a lot, sort of the level statistics gap ratio. I'll explain exactly what that is, how to calculate it, and what people expect to see in terms of the transition. Good. So if you recall from the morning lectures, Dima explained that there were 2 versions of localization, in some sense, that build off of each other. The first is that of non-interacting localization, which is synonymous with Anderson localization, and the second is that of many-body localization. Exactly identical to Dima, let's take a starting point, which is a tight binding model of particles hopping on a lattice, could be fermions, for example. So the Tij corresponds to hopping from lattice site I to lattice site J, and the omega I are the energies associated with occupying site I. As Dima explained, in one dimension, at least for nearest neighbor interacting spins, it turns out that Jordan-Wigner transformation ends up looking exactly like this tight binding model of fermions. The disorder in the problem is coming from the fact that all of these energies, omega I, for the different sites, are chosen randomly from a distribution. Here we've chosen to use a distribution that is uniform and centered at 0 between negative W and W. And if we think about it, what ends up happening in terms of the intuition is that as a function of the number of sites, so for example, there can be site 1, 2, 3, 4, 5. If we plot the energy of that site, omega I, this means that we naturally get situations where the energies are very different from each other because they're chosen from a particular disorder distribution. And the limit, of course, for understanding localization is really trying to understand what exactly happens in terms of how these Tijs, these hopping matrix elements, hybridize between these different sites. And of course, as you already learned from Dima, it turns out in the limit where this hybridization is very weak or the disorder is very strong, it turns out that one gets exponentially localized wave functions, and in the context of this specific Hamiltonian, it turns out this is Anderson localization. So let's answer question 1. What exactly does it mean for the system to be non-interacting? The first observation we make is that the model that we've written down, the Hamiltonian, is a quadratic Hamiltonian. And what I'll say applies to quadratic Hamiltonians of bosons or fermions. By quadratic, I mean there's only ever 2 operators. So we don't have the quartic operator, for example, that Dima explained was the presence of interactions. And the key is that in the context of this quadratic Hamiltonian, it turns out when one diagonalizes this Hamiltonian, so we go into a diagonal basis, this diagonal Hamiltonian can always be written as a sum over orbitals that we imagine running from 1 to n. Each orbital has an energy epsilon alpha, and I'm going to write the operators associated with the creation of a fermion within orbital alpha as d alpha dagger. Of course, diagonalizing in general is only a change of basis. It's always the case. So when we do this diagonalization, we naturally know that there's a relationship between our original orbitals that live on single sites in real space and the orbitals that diagonalize the Hamiltonian alpha, which are now going to be a change of basis. And in particular, this change of basis is going to correspond to every alpha being a superposition over my original basis, Ci dagger, with coefficients phi I. Maybe index this as phi I alpha. Okay. So having this diagonal Hamiltonian now allows us to expound a little bit on what we mean by non-interacting. In particular, non-interacting is precisely the statement that I can write down all of the many-body states of the system by simply looking at the occupation of my d alpha orbitals. So what I mean by this is I can think about every single alpha. So this is alpha equals 1, 2, 3, all the way up to n. And you can imagine now, we have n particles, there's 2 to the n states, any of these n orbitals can be occupied or not occupied. And once I have this set of orbitals, I can construct all of the many-body states by simply saying, okay, let's imagine that I've occupied my first orbital. Maybe I've occupied my third orbital, but not occupied my second orbital. Maybe I've occupied my nth orbital, etc. But the key feature of a non-interacting Hamiltonian, and which is satisfied by any quadratic Hamiltonian bosonic or fermionic operators, is the fact that the total energy of this now many-body state, many-body in the sense that now I have many, many particles, right? Many of these different orbitals being occupied, the total energy of this is simply the energy associated with every single one of these orbitals that are occupied. Feels very, very natural. Feels very, very natural at this point. Let's just recap very simply. We started with a Hamiltonian that describes fermions hopping in a disordered chemical potential. We can always make a change of basis to diagonalize. And in that change of basis, we have n orbitals. The change of basis amounts to our orbitals being expansions in the real space basis with some set of coefficients phi alpha. And now, in order to create many-body states out of these orbitals, one naturally imagines simply occupying these orbitals one by one. And the key feature now is that the energy of this many-body state, E total, is given by the sum of all of these. And herein comes the word non-interacting. The key is that there does not exist any energy terms that correspond to interactions between the occupied particles, the occupied orbitals. So this means that there are no energy terms like epsilon 1,3, epsilon 1n, epsilon 3n, etc. You might imagine, you would naturally expect that, okay, you can think about a generic physical system, that maybe you occupy one of these orbitals, and in order to occupy this orbital, you'd better pay the energy cost associated with actually creating a particle in that orbital. But you might also naturally expect, well, the influence of this guy living here means that there should be maybe another energy penalty or an energy gain, depending on if the interactions are attractive or repulsive, to be able to have that. And it turns out non-interacting localization is precisely the fact that in this context of quadratic Hamiltonians, those many-body energies are simply a sum of the bare single particle orbital energies and do not have terms that correspond to interactions between these orbitals. And this will not be true. This is no longer true if you add on a quartic term. So if you guys remember, in Dima's lecture, he added on a term that looked like density-density repulsion. Actually, I don't remember the sign. It was Ci dagger Ci, Cj dagger Cj, so it was density-density interactions. And this is a quartic term. Good. So maybe recapping some of the things that Dima mentioned, just to make sure that we are kind of going in a linear trajectory. In the absence of hopping, in the absence of Tij, all of the orbitals are trivially localized. None of the orbitals are talking to each other, so you basically have every single site being sort of a well-defined orbital by itself that never talks to anything else. But it turns out, as was explained, for sufficiently strong disorder W, one gets a property where the wave function of my single particle orbital, after diagonalizing this, looks like it decays from a particular site, Ri minus R0 alpha, over some length scale xi, and the xi is typically known as the localization length. Nothing dramatic's happened here, right? All we've said is, oh, wow, that's kind of cool, but nothing super dramatic's happened in the sense that if there's no hopping, then basically you have a part of orbitals that are just localized to real space sites. And now it turns out if the disorder is strong enough, it turns out that this hopping doesn't really have the energy to actually non-trivially mix sites. And because it doesn't have the energy to non-trivially mix sites, it turns out the relevant wave functions for the single particle orbitals, even after diagonalization, they no longer look like strictly delta functions on a single site, but they have an exponentially decaying envelope on some site. And the length scale of that exponential decay is given by xi, known as the localization length. Just for comparison, as Dima explained, this was his block wave limit. For comparison, if disorder is weak, it turns out the wave functions phi I squared look like 1 over n. So for any given orbital, it looks like it more or less has approximately the same amplitude over all sites in the system. And it turns out this is exactly what Dima explained leads to diffusive dynamics, and in this context over here, what leads to localized dynamics. Good. I see lots of smiles and nodding. Okay.
Maybe you'll explain it later, but so is the localization length can it be expressed as our microscopic parameters in the Hamiltonian?
Yeah, it certainly has to be expressed in terms of some microscopic parameter. So the microscopic parameter that's natural is the lattice scale. So usually the localization length is expressed in terms of some number times the lattice scale. But that's, yeah, it's some parameter that certainly depends on the lattice scale. And that is, I mean, that's the only length scale that we have in the problem.
Yeah, like also like the disorder strength and other stuff, because like...
Yes, it can. Yes, it can. Yes, it can. We won't go into detail on this, but there are, yeah, at least in the single particle case, there's phenomenology. Okay. Yeah, please.
Is this only true for this Hamiltonian, or also if I allow higher order tunnelings, like...
Higher order tunnelings, like what? What do you mean by that? Actually, I see. You mean you keep this quadratic, basically, but you actually have, like, let me just make sure I understand what you mean. So maybe you have another term that's not nearest neighbor, but next nearest neighbor.
Yeah, exactly.
Like T prime I-K, C-I dagger C-K, right? Yeah, so long as all of these objects are quadratic, it's okay. As long as it's quadratic, it's okay. But it turns out the important thing is that here it's still sort of finite range. If you allow for this tunneling, if you actually imagine that the tunneling really has some long distance tail, so if you actually say, actually what's happening is that the tunneling is happening because of microscopic Coulomb interactions. And now I have a tail that looks like a power law, then things get much more hazy. Not quite as clear, but at least in this case, you feel free to add on a next nearest neighbor term as long as it's finite range and nothing changes. So the case of many-body localization, and I'll write down effectively the same Hamiltonian as DEMA, but maybe slightly differently, which is that I'm going to rewrite it in the context of these orbitals over here. So what I'd like to imagine doing in our minds is, quite a few Russians, so we should do perturbation theory, and we're going to imagine trying to do perturbation theory in the strength of some interaction V. Okay? So naturally, the first thing you do is you diagonalize your Hamiltonian, and after you diagonalize your Hamiltonian, I'm going to expand my interaction in the basis set by my localized, Anderson-localized single particle orbitals. So the natural Hamiltonian one expects there is the first term had better be our Anderson Hamiltonian, epsilon alpha d alpha dagger d alpha. And when I re-expand my interaction, I'll naturally get a term, sorry, let me just write it in the next line, a little bit more room. Everything's smaller here, even the eraser. So we'll have, it's not quite as entertaining as John's lectures, but you know. Queen to B8. Guys, come on, follow.
There's a bishop in the way.
The bishop, well, you know. Okay, so. Good. So what I've done here is this type of a quartic interaction, which is written in real space. What I'd like to do is I'd like to re-expand it in terms of the orbitals, these d alpha, sorry, these should all be d's. Excuse me. What I'd like to do is re-expand it in terms of these single particle wave function orbitals that I have, and naturally you'll get an interaction strength that has orbitals, and the orbitals can all be different. In real space it looks like density, but once I go into this new single particle diagonalized basis, it certainly doesn't have to look like that. And that is, in some sense, the most general many-body localized Hamiltonian that one can start with, that has an Anderson localized piece and then a many-body interaction piece, which corresponds precisely to the quartic term that Timo was talking about. What I'd like to do now is to give some intuition for the role of this interaction V. And the key point is, in some sense, what we'd like to have, the thing that you learn from DEMA, is that when one's in the Anderson localized phase, there's no transport to the problem. There's no dynamics, there's no transport. And transport is basically arrested because of the disorder in the problem. So we'd like to understand for ourselves how exactly, what's the intuition for why this type of interaction allows for non-trivial transport to happen. And the intuition, of course, is to try to understand when this interaction will be able to mix different orbitals and to be able to allow particles to move in some non-trivial way, which previously we thought wasn't allowed because of a lack of transport. The first thing we can immediately know is that if we look at the matrix element associated with this interaction in these orbitals alpha, beta, gamma, delta, if I take two of the orbitals to be much further apart than the localization length, then this matrix element has to decay exponentially, trivially, simply because of the real space piece. Right? The real space overlap is going to be small, so that has to be small. So what we'd like to do is let's start by thinking about some length scale in the problem that's of order the localization length, and ask ourselves, how do we understand transport being generated intuitively by this interaction within this length scale? We can imagine that there's exponentially localized orbitals, and the length scale of each of these orbitals is localized over some length scale xc, the localization length. And the key intuition is that one can basically imagine having a situation where one borrows energy. So gamma here, we're annihilating something in gamma and moving to alpha, annihilating delta, moving to beta, for example. We can imagine that we have a configuration where we actually annihilate the gamma, the particle that lives in gamma, bring it to alpha. So this costs some energy. But at the same time, we can compensate for that by taking us from, let's say, delta to beta. So this, in principle, allows there, that's exactly why this interaction term allows there to be possibly non-trivial transport. Because instead of saying that, oh, this process is just trivially off-resonant, there's now a way to borrow energy from a different process, and in combination, the combination of these processes needs to be resonant, and not just one of the processes by itself. In particular, one can imagine that the resonance condition ought to be that the energy difference, epsilon alpha plus epsilon beta, minus epsilon delta, minus epsilon gamma. Oh, sorry, these should be epsilons. E and epsilon will be synonymous. The condition that this is resonant is simply that the energy difference of this chordic process should be smaller than the matrix element associated with this interaction. And this gives me many, many more ways to actually have transport, starting at small length scales of order the localization, like by borrowing energy from one of these processes and giving it to another process which maybe did not look resonant in the first place. So the interaction term means that things that in the Anderson localized non-interacting case didn't look like they could help each other now have a matrix element where the resonance condition is much, much less stringent. And this also maybe answers one of the other questions that kind of came up, which is why is everything that we're discussing in terms of many-body localization at finite energy density? And the statement is because at zero energy density, there's none of these processes. There's no occupation of any of the orbitals except the lowest orbitals. Right? There's no occupation of any of these. There's nowhere to borrow energy. But at finite temperature, or at finite energy density, there's many ways to borrow energy. Right? So the intuition is simple. When you're at very, very low energy density, there aren't any of these higher processes that are already occupied. So there's nowhere to borrow energy from, which is why we typically think about the physics being at finite energy density. Good. And of course, one can follow this perturbation theory to the end, as Dima sort of alluded to, and the convergence of this perturbation theory is a statement, at least in principle, on the self-consistent, whether or not many-body localization is consistent. It doesn't tell us necessarily that many-body localization happens, but it tells us perhaps that it's consistent as a phenomenon.
What does consistent mean?
Sorry?
What does consistent mean?
Consistent means that the perturbation theory converges, that it doesn't break down such that if you assume that your system is localized, that you end up at a localized point. So it doesn't really tell you that actually any given Hamiltonian has to many-body localized, but if you work within starting with the single particle Anderson localized assumption, then you find out that that assumption holds and that the perturbation theory, the interaction, does not lead you to delocalization, if it's small enough.
I see. So you're saying if you started in an Anderson localized state,
that's right.
adiabatically turned on.
Exactly. So we're always thinking about this consistency argument. We're always thinking about doing perturbation theory in the interaction stream. So let me do a very, very specific example. Or at least let me write down a very specific example. And in this context, I'll just give kind of a working numerical tool for how people characterize this, that hopefully, for those of you that are interested in reading papers, this will be a very, very common diagnostic for many-body localization. The specific example is one that's been studied for many years. Is a really nice paper by Arajit Pal and David Hughes from back in 2010. And the model is exactly what Dima wrote down. It's a spin 1/2 model. And here, Dima split apart the flip-flop piece and the interaction, the ZZ interaction piece. I'm going to keep those together so that we have sigma I dot sigma I plus 1. So it's a Heisenberg nearest neighbor interaction. You can split this into an XY piece that's Dima's flip-flop and a piece that's ZZ, which is what we call the interaction. And imagine now having a random field in the Z direction. So again, this is a spin 1/2 system. As I mentioned yesterday, trying to look and understand the physics of localization in these models or of thermalization in these models is pretty challenging, and people are typically limited to exact diagonalization of the entire Hamiltonian for system sizes up to perhaps approximately 20 spins. So let's ask ourselves a question. How do we diagnose the MBL transition? The MBL to EGH transition. And perhaps the most standard way to diagnose this is something that Dima mentioned, but we'll explore in a little bit more detail, is the notion of level repulsion. And the intuition for this level repulsion is extremely simple. When you have a many-body system, and the many-body system cares about, is in a thermal state and where particles are able to talk to each other, in some sense, many-body localization is the fact that really there's no transport in the system, and thus there's actually very, very little ways for the different regions of the system to sort of interact with each other in a non-trivial way. In the context of diffusive systems, or systems that are ETH, aka thermal, level repulsion is specifically the fact that if you look at the full many-body spectrum, so these are 2 to the n many-body states that live in an extensive spectrum somewhere between n and minus n in this case, that it turns out the level spacing between these, this P of S that Dima was showing, the level spacing between these different levels never gets too close. And the reason why the level spacing never gets too close, you can think about very simply in terms of a 2x2 matrix. If the two levels get very close, as soon as there's a matrix element that couples these two levels, they immediately split by at least, at minimum, the size of that matrix element, right? So in general, as long as you have an interacting system where interactions dominate and you're not localized, it turns out that levels never want to get too close to one another. In a system which is localized, on the other hand, it turns out that the matrix element is extremely small, or has very, very low impact. And because of that, levels can kind of get arbitrarily close to each other, and it's the statistics of these levels that is what people mean when they talk about level repulsion. So let's be very specific about how, if you wanted to go about diagnosing many-body localization on your computer tonight, how you would do it. Step 1, you would choose a given disorder realization. And I'm going to call that disorder realization lambda. What I mean by that is because these HI, sorry, I should have mentioned this, these HI are what encode our disorder, we'd better pick for every single spin a random value between minus W and W. So you start by making that choice for however long a length chain you have, and you call that your initial disorder realization. Step 2, you diagonalize your Hamiltonian and find the full many-body spectrum, all 2 to the n eigenstates, and you sort them precisely like this, from lowest energy to highest energy. Step 3, you calculate the gap between every single pair of eigenstates that you've now found via diagonalization. In particular, we now have delta lambda, this is in disorder realization lambda, for eigenstate n. The gap is going to be E lambda n minus E lambda n minus 1. So these energies are indexed E1, E2, E3. Lambda indexes the fact that we're in a specific disorder realization, and the gap between adjacent energies is precisely now another index delta n. And a statistic that oftentimes you'll see in papers is something known as the gap ratio. And this gap ratio, so you have many, many delta n's corresponding to every pair of gaps, right? And this gap ratio is precisely when you look at an adjacent pair of gap values, you take the minimum value of delta lambda n plus 1 divided by the maximum. So looks complex is ultra simple. So basically, for every pair of gaps over here, you ask yourself which one's larger. You put that one in the denominator and you put the smaller one in the numerator, and now you have a new statistic called the ratio Rn, n which indexes the fact that for all 2 to the n states, almost all of them, missing one, almost all 2 to the states, there's one R for each of those. Lambda, which indexes the specific disorder realization, you calculate the statistic known as the gap ratio. Step 4, you compute the average of this gap ratio over the states, over the energy eigenstates in your given disorder realization, and over disorder realizations as well. Okay? So you compute the average of this ratio over all of the states within your single disorder realization, and then you pick a new disorder realization, and you do the same thing, you average this over and over. Once you compute that average, it turns out that exactly coming from the microscopic intuition related to level repulsion, in the delocalized or ETH phase, compared to the MBL phase, one has 2 different expectations. And in particular, in the delocalized phase, one expects the average R to be approximately a value 0.53, satisfying something known as GOE statistics. And in the localized phase, the average R is approximately 0.39, satisfying coming from Poissonian statistics. So super operational way for how to calculate whether or not a system is localized or not. And now let's ask ourselves, what do we expect to see in a set of numerical data, for example, as a function of the disorder strength and R? So at small disorder, we don't want to really work where disorder is 0, because this model has the sad property that when W is 0, this model is integrable. So when I say small disorder, I'm really thinking finite disorder away from 0, but small so that you're not localized. In this case, we'll have things start off in the delocalized phase for weak disorder at 0.53, and we'd hope that things end up in the large disorder case at 0.39. But exactly as both myself and Dima have emphasized in the last couple of lectures, the existence of a transition between ETH and MBL is fundamentally a statement about the thermodynamic limit, which means that if you look at any finite size L, which L equals 20 is certainly a very finite size, what you'll generally see is something that looks like a very smooth crossover. So if it looks like a crossover like this, how the heck can we know whether or not there's actually a phase transition? It turns out what we'd like to do is a technique that's often used in the context of phase transitions known as finite size scaling. In the thermodynamic limit, if we believe there is a true transition, then what we actually expect to see is that at some value of W critical, there really is a sharp jump in the behavior of this level statistic ratio, right? That's what it has to be if there really is a transition. But actually then, as you increase system size and get closer and closer, that sharp jump should manifest as something which looks like these curves, in fact, get sharper. So, despite the fact that every single one of these individual curves is a smooth crossover, you never see a distinct jump. by looking at the way that the system changes, the behavior of R changes as a function of scaling up the system size, it turns out one expects to see this sharpening if there really is a phase transition. And this is what people mean when they say they're performing finite size scaling to explore the critical point between many-body localization and eigenstate thermalization. Good. Good. Any questions thus far? Yeah, please.
So, I understand this diagnostic procedure, but why does it work? Like, not finite size basis.
It works because of, all right, so maybe I didn't explain it super well. It works because of level repulsion. So, what level repulsion says is that in the thermal phase, in the ETH phase, the property is that, the key property is that, and the difference in these two phases is that in the ETH phase, these levels never get too close together. Whereas in the MBL phase, the levels kind of don't care about each other and can get arbitrarily close. So this procedure is just some way to mathematically formalize that intuition, right? So I'm telling you that something that matters is basically the property that you'd like to somehow zoom in on is the property of what exactly, of how close levels get to each other. How close levels get to each other, a natural thing to look at is the gap between levels. And then it turns out this ratio has a very, very nice property because it turns out it has this finite size scaling type property. Yeah. First.
So are you just taking an average over many disorder realizations because over some particular realization you might not get levels close to each other, but if you then do it?
Yeah, maybe that's sort of the right intuition. The reason is that, in some sense you have a disordered problem, so you'd like to understand what the typical behavior is. And it turns out you may be unlucky such that your random number generator just generated 20, 20, 20, 20, 20, 20, 20. Then in that case, even though the disorder looks extremely large, it turns out your particular realization is really crappy and you're not going to get something that looks localized. So you average over disorder realizations to basically coarse grain out that. Yeah, and then
for this finite size scaling, do you just need a tendency that it gets sharper, or does it have to get sharper in a certain scaling with L?
That's a good question. So the expectation is that the way it gets sharper as a function of system size tells us something about the theory of the transition. It turns out one of the open questions in the field, and something that I think Dima's worked on quite a bit, and my colleague at Berkeley, Ehud Altman, has worked on quite a bit as well, is trying to understand that. So in principle, the existence of a phase transition, all I need to see is that it gets sharper, and the sharpness is really what would be ideal is to see that the crossings all kind of happen at one particular place, and that corresponds to this critical, this W critical, but actually trying to rescale all of these curves kind of onto some universal curve, and doing that using the system size to an exponent 1 over nu is very important for understanding the critical properties, or the properties of that phase transition. And it turns out that is a poorly understood phase transition and an interesting question. Please.
Is there a reason these values saturate to those particular things? Or at least like, the ratio between them, or what percentage difference you expect between like far apart and closer together?
There's no God-given reason. This is not like some factors of pi and alpha, the fine structure constant multiplied together. No, it really is, it's a property of basically random matrix theory, it turns out. If you actually take a matrix and you literally put elements into the matrix, randomly taken from a Gaussian, you will get this. That's why people call this it's Gaussian orthogonal ensemble. And here, if you do the same thing, but you choose things sort of in a Poissonian distributed way, if you choose the levels in a Poissonian distributed way, you get a different statistic. But there's nothing like, the percentage difference between this does not tell us something about how quantitatively different the MBL and ETH phases are. I think that's not the right way.
Okay, so then if I had some arbitrary model, then I would really just see if I could get two values of these that were like different, with the lower one corresponding to some MBL phase, and see if there's some sort of transition.
Yeah, and basically if you take any model that you've more or less studied that is not many-body localized, and you did this procedure, you always get out 0.53. And the models that look like this are models that actually are not ergodic, so maybe are either integrable or are localized in some way. I should emphasize, I think, one point that Thierry brought up. Everything I'm thinking about here is sort of averaged over the entire spectrum. One has to be careful. I mean, there are questions if one averages over, one looks at specific windows of energy density, and does this averaging procedure, for example, not over all of the eigenstates, but starts off windowing this piece of the energies, this piece of the energies, this piece of the energies, and then, but still does the disorder averaging. But when windows the energy densities, one can see something perhaps different happen. At the moment, I've chosen to work with systems where we're imagining that the disorder is large enough such that the entire spectrum has this property, or we're looking just at the infinite temperature version of this. Good. So, interesting. Let's see. So there was a question that I'll probably then get to in the beginning of tomorrow's lecture. There's one question, I don't remember who asked it, about what happens when, for Manybody localization, higher dimensions, and what happens when you have processes that Dima called avalanche processes. These are related to the physics of rare regions, so-called Griffiths physics, and I'm planning to give an explanation in terms of both limits of Griffiths physics tomorrow, the limit that leads to subdiffusion, and also the limit that leads to the avalanche. But first, I'd like to follow up on something that Dima mentioned, which is really a very powerful, I think, perspective on how to think about localization in terms of quantum information. And what I'd like us to keep in mind is the following setup. Let's imagine that we have physically a one-dimensional chain of spin 1/2 particles. And let's imagine that the spins are interacting with each other, some generic Hamiltonian. And let's imagine that we prepare a pretty hot initial state. Okay? So, for example, you could try to look at a situation where the density matrix more or less has no structure to it. But so we don't want to be preparing a low energy eigenstate. We can imagine a hot initial state. The limit is, of course, having an infinite temperature initial state. And we want to ask ourselves a question. Comparing phases that are ETH to phases that are Anderson localized to phases that are Manybody localized, how can we understand these three phases in terms of storage of information? Note that I haven't specifically said that the information has to be quantum yet. I've just said we're thinking about this in terms of the storage of information. But we have quantum spin 1/2 particles, so let's give a procedure. Let's imagine that we prepare spin I in some state that looks like alpha up I plus beta down I. And we'd like to ask, how do the degrees of freedom in these three different phases behave as memories of information? How do the degrees of freedom in these three different phases, in these phases, behave as memories of information? Okay. And in particular, the question one can ask is, if one makes a local measurement on spin I at some later time t, can one recover the information that one initially encoded in that spin? It's literally the question you would naturally ask if you were asking, how good does a spin behave as a memory? Let's define a proxy that we'll like to look at as a function of time. And the proxy that we'd like to look at, one proxy that one can look at is the autocorrelation function of the spin at site I a 2-point autocorrelation function between 0 and t, where this alpha, oh sorry, I've used alpha twice, excuse me. Let's use eta here, where eta is x, y, or z. Every quantum spin is described by a basis that is sigma x, sigma y, and sigma z. Actually, because sigma x and y, sigma x, y, z equals identity, you only really need to know the behavior of 2 of them to know the behavior of the third. So the correlation function that I'm looking at should be super intuitive. If it doesn't make sense, you should ask. The types of correlation functions that I'm basically looking at are things like sigma zi of t, sigma zi of 0. This exactly tells you if I had stored some information, some polarization information in the z direction of the spin at 0, how much of that polarization information is remnant in the z direction of that same spin at time t. Right? Exactly the question, how good does this degree of freedom behave as a memory of its initial condition? And the fact that I'm tracing over this is basically the statement that I'm actually doing an average, or I'm taking the expectation value over an infinite temperature state.
Can I ask a question?
Yeah?
One might imagine a situation where the information still stays in that spin, but processes in time in some deterministic way.
Processes in time in some deterministic way.
So you're just looking at, say, the z components.
Sure, yeah,
right?
exactly.
You could imagine that it, like the information evolves.
Yeah, okay. I think I know what you're trying to get at, and I think it'll be answered in the course of this next piece. Yeah, I think so. But if it isn't, you just ask it.
Okay.
So, what we'd like to look at is, for example, this particular autocorrelation function, and understand the behavior of this autocorrelation function as a function of time. And let's start with this case. Let's call this case 1, the ETH case. We store some information, and what we expect to find, if the initial state has no polarization built in, is that actually maybe we start off with, let's say, any of these correlation functions. So maybe let's say we're looking at the ZZ correlation function. It'll start off perfectly because sigma z squared is 1, and then it'll have some dynamics, but eventually decay in the ETH phase. And this will be some time scale that corresponds to some decay time. And this is what we mean when we say that we expect in the ETH phase a spin to decohere on some time scale, and this time scale to be given by approximately 1 over j. Let's say, put a interaction strength between these spins by j. And in some sense, this is the stat-mech version of what people mean when they talk about decoherence. All that's happening is that the single spin degree of freedom is actually becoming strongly entangled with all of its neighbors. And as it becomes strongly entangled with all of its neighbors, since I'm trying to recover the information at time t using a local operation on spin I, that doesn't become possible anymore. Super intuitive. Let's always use solid lines for ZZ correlation functions. I told you that because x, y, and z multiply to the identity, it turns out that I only need to look at some 2 of the 3 correlation functions. We'll use dotted lines for the xx correlation function. And we find that, in general, in the ETH phase, both of these correlation functions decay on some characteristic timescale set by the interaction strength in the system. Supernatural. You don't expect to be able to store any information in a system that thermalizes. That's why you don't, in general, have strongly interacting many-body systems being quantum computers. Right? You know, quantum computers for, everyone wants isolated ions, isolated atoms, isolated superconducting qubits. That's the reason, because if you have strong interactions, initial quantum information that's stored locally decoheres, and that decoherence is simply the entanglement of that information with many, many degrees of freedom driven by the interactions of the system. Good. Lots of nodding. Very good. Let's now try to understand case 2. Okay. So case 2, so let's imagine here that the Hamiltonian that we have is precisely this Hamiltonian. So let's call this HS. So case 1 is HS where W is less than WC. Okay. So when the disorder is smaller than the critical disorder strength, HS is in the ETH or thermal phase. Let's try to look at, case 2. The same Hamiltonian where W is greater than WC. What we'll find is, in fact, now the behavior of these two correlation functions will be different, and this difference will come effectively from the fact that my disorder is actually in a particular direction. The spin-spin interactions look like they're SO3 invariant, but the disorder is chosen a specific direction. And what we'll find is that the ZZ correlation function, so sigma Zi of t, sigma Zi of 0, let's just take the trace of this, looks like it'll initially have some decay, but ultimately will saturate at some finite value that's order 1, even as the system size is taken to infinity, even as L goes to infinity. So this plateau is not a function of system size and doesn't decay. On the other hand, the X correlation, one will find, actually slowly decays as a function of time and eventually reaches 0. It turns out this is the case of, of course, of Manybody localization. The origin of this decay is precisely the dephasing or the logarithmic growth of entanglement that Dima explained was kind of one of the paradigm features of Manybody localization. And in fact, in general, we expect such a correlation function to decay as a power law, coming from the fact that it gets entangled with more and more spins in this logarithmic fashion. And the size of those, Hilbert space of those spins goes exponentially large, and the volume of that entanglement region, so that log and the exponential lead to a power law. But what this tells us is that, in this case, the Z component always stays. So if I had a spin in the Z component, if on average the spin at site I was up or down, I will know that. So this is what people mean when they say that in a many-body localized phase, each spin stores a single classical bit. AKA, each spin behaves as a classical memory. So in the ETH case, we think of each spin as not storing anything. Each spin doesn't behave as a memory at all. In the many-body localized case, we have the property that the ZZ correlation function, the same reason that the many-body localized phase has a lack of conductivity or a lack of transport, is precisely why, well, spin's not transported, which is why we have the plateau in the Z behavior, but in the X behavior, this logarithmic dephasing corresponds to our phase information being lost, and that phase information being lost is exactly what it means that we only have a classical bit as opposed to a quantum bit. Let's modify the Hamiltonian that I just erased. So let's modify the Hamiltonian that we just erased a little bit, and let's write down the Anderson localized version of that Hamiltonian. What I'm going to do is I'm going to simply drop some of the terms of the Hamiltonian, and in particular, I'm going to drop the ZZ piece. So if you remember, HS previously in your notes was sigma dot sigma, which is an XX, a YY, and a ZZ component. All I'm doing now is dropping the ZZ component and leaving nearest neighbor XY interactions. In Dima's language, I think he wrote this as sigma plus I, sigma minus I plus 1, plus Hermitian conjugate. And that's when you use the raising, put in the raising and lowering operators. I'm probably off by a factor of 2. But in this limit, again, it turns out that if one makes the transformation to fermions, one gets back to the non-interacting limit that I was talking about. And so in the large disorder case here, when HI or in the 1D that doesn't matter, but we could think that we're working in strong disorder. In strong disorder, this actually is in the Anderson localized phase. So 3 very simple Hamiltonians. The first was Heisenberg interaction, where the random field was weak. The second was Heisenberg interaction, where the random field is strong. And the third is Heisenberg interaction dropping the ZZ piece. And these 3 Hamiltonians live in the ETH phase, the MBL phase, and the Anderson localized phase. And if we now look at the same correlation function, so again, the ZZ correlation function, the XX correlation function, we expect for the ZZ correlation function that much like Manybody localization, will have sigma alpha of t, sigma alpha of 0, the autocorrelation function. We'll have it basically plateau to an order 1 value. But it turns out, precisely because of the lack of interactions and the lack of this logarithmically slow entanglement growth, it turns out there's no dephasing either in the Anderson localized system. Precisely because there's really no interactions, no scattering of the particles, there's no dephasing, and this means that the XX correlation functions and the ZZ correlation functions both plateau to finite values in the thermodynamic limit. And this is what people mean when they say that in the Anderson localized phase, each spin stores a quantum bit. Again, it's a kind of a, basically it's a way to nominally have spins that are talking to each other, but to use disorder to make them not talk to each other such that they more or less behave like isolated qubits.
What is the scaling of the T alpha for NBL and
Where's T alpha?
the turnover time. So
I don't know what you're talking about.
Where you start to like go to plateau, you know.
No, this time scale, I see. So this time scale is typically going to be aborted the local interaction string. So it's typically going to be something like the local interaction string. It's basically the time scale where there's sort of dynamics that kind of locally thermalize, and once the local thermalization happens, which is more or less on the length scale set by the localization length, which is going to be some number multiplied by 1 over j, then things have reached the plateau. Please.
So in this Anderson localization combinatorial, if you turn on like the ZZ interaction gradually, would you see like similar thing as what you are erasing right now as a base
Yeah, so okay, fine. So if you turn on for epsilon small ZZ interaction, for arbitrarily small ZZ interaction, it turns out you will start to dephase this, and in the long time limit, this XX correlation function will go to 0. No matter how small, there is not a finite value of the ZZ interaction that this can tolerate. So this quantum bit basically dies for any value of ZZ. Here.
How do you know?
Let me see. I guess in the, I think about it, if I think about it once I go back to sort of this interacting picture, you'll have some finite V, and this V will basically start to dephase you.
No, I'm not disputing the results. I was curious to know if there was some derivation or some.
I don't know that I don't know that that question has been asked in this language before, in this specific language before. But the intuition has probably got to be right, which is that as soon as you turn on ZZ interactions, you have a quartic term, and that quartic term will give you some small matrix element, and that matrix element will slowly start to entangle you, and on some time scale you lose this. But I don't know if there's, I don't think people have thought about it quite in this language or analyzed the specific decay of such correlation functions.
Yeah, because this is simple argument, so if you have sort of start from another insulator, put some particles, they will be superpositions of nearby localized orbitals, and then interaction is very weak. The only thing you can do is sort of start a direction, right? And then the net value will be immediately without that. I would say that argument actually works the best when the interaction is weak, because then it's just hard here and you don't need to worry about anything else. Right now, would you agree?
Yeah, I agree. Okay, so I kind of gotten to the end, but I think actually the thing that, if I don't do this now, you'll never see it. So it turns out, or you'll read it in my lecture notes, but I think one of the most interesting consequences of many-body localization is the fact that really working off the statement that Dima made and emphasized at the end, the fact that you have area law in eigenstates gives you the intuition of doing localization protected quantum order. And if, we can take a, you have to raise your hand this time. We can take a straw vote. Would you be interested in having me spend 30 minutes just going through a very specific example of localization protected quantum order? Or is everyone so totally messed up that you'd rather me not? Who would like to see the derivation?
A 15-minute version.
Sorry? Well, go back to chess. So remember what Herr Professor Dima Bonin emphasized is really that one of the special properties of many-body localized eigenstates is that we have area law entanglement. Area law entanglement in eigenstates. And what Dima emphasized is precisely that usually, so maybe there's a couple of references, well, the references are in my notes, you'll find the notes online, so I won't write down all the archive numbers. The other place where we often see area laws is typically in the context of gapped ground states. So this begs a very, very interesting question, and the possibility that we'll work through explicitly now. It turns out this possibility is not really proven, I would say, but it has numerical support for it. And from my perspective, I think it's maybe one of the most important consequences of many-body localization moving forward. The interesting possibility is whether or not can localization enable what we typically think of as ground state physics or ground state order to occur at higher temperatures. And this is particularly ideal in the context of all of these isolated AMO systems that we've been thinking about, because it would really mean that perhaps some of the order that one can hope to see, which is typically one thinks of in condensed matter physics, as being ground state, that really one can see it in higher energy eigenstates as well, and that would be really powerful. What we're going to do now is do a very, very my favorite personal case study of this problem, and one that I've worked on a lot, which is now related to this question over here. How do we make a quantum memory in an interacting system at infinite temperature? Okay. How do we make a quantum memory in an interacting system at infinite temperature? So let's juxtapose. The two interacting cases were here on the left-hand side of the board, and we learned that neither of them is a quantum memory. One of them is no memory, and the other is a classical memory. So the case study we'd like to ask ourselves is, how do we make a quantum memory in an interacting system at infinite temperature? And the specific example we're going to consider is that of one-dimensional, symmetry-protected topological order. It's okay if you don't know what that means. We'll go through line by line the derivation. Let us imagine that we're given a Hamiltonian H0, which looks a little bit funky. Our situation, as we've been doing for a long time, is still a one-dimensional spin 1/2 chain of particles. And now we're going to have the interactions between these spins be of the form sigma z on site I-1, sigma x on site I, sigma z on site I+1. For those of you that are familiar, it turns out this will be very, very much analogous to the so-called Haldane or perhaps AKLT phase in terms of its topological nature. But at the moment, I've written down what looks to be a super simple Hamiltonian. It only has one type of term. It turns out that type of term is a three-body interaction, Zi-1, Xi, Zi+1. And we'd like to start by making a few observations about the model. The first observation is that the S in SPT stands for the fact that there exists a symmetry. What do I mean by symmetry? I mean that there exists some operator which, when I conjugate the Hamiltonian by that operator, it doesn't change the Hamiltonian. Very natural definition for a symmetry. And it turns out there are two symmetries that one can look at. The first symmetry operator is given by the product on all the odd sites of sigma xi. And the second symmetry is given by the product of sigma xi on all the even sites. These two, because these are chains of Pauli operators, and every single chain of Pauli operators squares to the identity, P1 squared squares to the identity, P2 squared squares to the identity. This means that the eigenvalues of this operator are only allowed to be plus or minus 1. So the eigenvalues of this operator are allowed to be plus or minus 1. And because there are two such operators, people say that the symmetry of this Hamiltonian is given by Z2 cross Z2. Even if you're not familiar with this general framework, you should be able to follow everything I'm saying. Right? You have a Hamiltonian, there's a symmetry of the Hamiltonian, which means conjugation by an operator doesn't change the Hamiltonian. You can check, but I've written down explicitly what the two symmetry operators are. They have the property that because they're products of Pauli operators, they square to the identity. And since they square to the identity, their eigenvalues are plus or minus 1. And because the eigenvalues are plus or minus 1, there's only two values of the symmetry operator. We say that each of these gives you one integer mod 2 classification and another integer mod 2 classification. Okay, coming from P1 and P2. Good. Okay. So it turns out, we'll go through another quick observation. So let's be specific. Another observation about the model is it turns out that each term in the Hamiltonian H0 commutes with all other terms. For those of you that are familiar with this language in terms of quantum information, people typically call such Hamiltonians to be in the stabilizer limit. You can already see this, so let's draw these dots as our spin 1/2 1D chain. If you have two ZXZ operators that do not overlap in terms of the number of sites they occupy, they certainly commute. The only other possibility is that they overlap on two sites, in which case Z and X anti-commute here, Z and X anti-commute here, which means the two operators actually commute. The last possibility is the fact that they overlap on one site, and if they do, they can only overlap via Z's, and that also must commutes. This tells us that every single term in the Hamiltonian commutes. Let's call these terms, let's say that these are actually operators lambda I hat, so these are operators. So we have the property that all lambda I, lambda j commute with each other, and also because of that, each lambda I also commutes with a Hamiltonian. Good. So, what are the consequences of these two observations in terms of the topology of the model? It turns out the consequence, of course, is that because all of these commute with each other, I'm allowed to index the Hilbert space of my Hamiltonian H0 using the eigenvalues of the lambdas. Right? I can literally, these are all operators that commute with the Hamiltonian, so that's a good basis. Just as I said that all the P operators there were actually products of Pauli operators which always square to the identity, lambda is a product of Pauli operators, 3 of them in particular, which means that lambda also squares to the identity. So lambda I squares to 1, which means that lambda I can either be plus or minus 1. and I can index almost my full Hilbert space by simply picking whether the lambda i's are equal to +1 or -1. That's exactly what you would do, to solve this Hamiltonian. It turns out that one might say, okay, that's fantastic, so we solved the problem. All of the many-body eigenstates of this problem are basically saying that, okay, let's choose our string of lambdas. So maybe lambda on the first lambda is given by +1, the next lambda by -1, -1, +1, dot, 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 right? So that's how we would want to specify some many-body state. Okay? But what we notice when we try to specify this many-body state is precisely the fact that the number of lambdas, when one has an open chain like this, the number of lambdas that one has in a system does not fully specify the Hilbert space. So we have n spin 1/2 objects, which means that the expected Hilbert space is 2 to the n. Let's count the number of lambdas together. There's 1 lambda here, 2 lambdas here, 3 lambdas here, 4 lambdas here, 5 lambdas. But you notice that actually the chain has 7 particles but only 5 lambdas. And this will always be true when one has open boundary conditions. For open boundary conditions, it turns out the lambdas will specify 2 to the n minus 2 states of the Hilbert space, and it will miss 4 states. 4 tensor product states of this. It turns out the remarkable thing, as you can kind of already see, and what I emphasized by having open boundary conditions, is that these states live on the edge. So it turns out there actually exists 2 decoupled, this is the topology of the model. The topology of the model, and this is how we're seeing it, is the fact that there exist 2 decoupled spin 1/2 modes, one at each edge of the system. Okay? One at each edge of the system. So I can write down what those operators are. In the interest of time, you guys can look at that in the notes. But now let's get on to the final couple of minutes just to explain where many-body localization comes into this. So it turns out that the fact that there exist 2 decoupled edge modes means precisely that we have a one-dimensional system, and this model has, right, there's no disorder in the model whatsoever. It's a stabilizer limit of a model, and the model has 2 decoupled spin 1/2 degrees of freedom at the edge. And this is, in some sense, the same edge modes that one is familiar with for the Haldane phase, although that model is a spin 1 model. So what does the many-body spectrum look like for this model? Well, it turns out because these 2 edge modes are decoupled, I can have the edge in any state down, 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 up, up, down, up, and it's decoupled from the rest of the entire Hamiltonian, which means that the many-body spectrum, the 2 to the n states, arrange in quartets, like this. Every single eigenstate comes in with 4-fold degeneracy, and the 4-fold degeneracy comes from the fact that actually, in addition to the state that lives in the bulk, I can choose any pair of states that I want for the edge modes. In principle, this means that I can store quantum information in the edge at any temperature. At least for this model, I can store information in the edge at any temperature. So I can encode information in this. It's trivially decoupled because I have a fully commuting Hamiltonian. It's trivially decoupled from the bulk of the system. So I'm allowed to store a single bit of quantum information in each of the edge modes, and I don't care what temperature I'm at because there's no scattering of the bulk whatsoever because we're in the limit where everything commutes with each other. Okay. But of course, this is a particularly particularly fine-tuned limit of the problem. So this is extremely fine-tuned at the level of what we would say is sort of integrable. It's a stabilizer limit, and it is integrable. In principle, if you add any perturbations that make the model non-integrable, that make the model not in the stabilizer limit, you immediately lose this property. So let's write down a modified Hamiltonian. That's our original term, sigma zi, sigma x, zi minus 1, sigma xi, sigma zi plus 1. Let's write out a couple of other terms that we could have, a local field, you could have spins interacting with each other, and these h and v can be as small as you want, but we're going to take the thermodynamic limit. The only thing, of course, is that the additional terms I've written still respect the symmetry that I had written down here. Okay? So one important thing is the terms I've written here still respect the two symmetry operators I wrote. So it doesn't change the symmetry class of the problem, but I've now made it a totally strongly interacting non-integrable system. The Manybody spectrum now looks like this. You'll find a fourfold ground state degeneracy with some order 1 gap, where 1 is measured in units of J. But the excited states of the spectrum will be totally, it will not look like any multiplets. They'll be very, very mixed and won't have any order whatsoever. There will be no finite gaps between them. The gaps between them will close exponentially as one increases the system size. There's no notion of this kind of well-defined multiplets anymore. So this is what we typically think about in condensed matter physics as being a ground state topological phase. Okay? This is what we mean when we say that we have a ground state topological phase. In the sense that if one has temperatures below the gap, then the system is only occupying this ground state space. And in particular, there really are no thermal excitations in the bulk to scatter information on the edge. And in this limit, then we basically have that again, when temperature is less than the gap, we can store a quantum bit on each edge. But for any temperatures above the gap, one cannot store a quantum bit on the edge, because that's going to scatter with the thermal excitations, because we no longer have this extensive set of conservation laws that tells us that all of our thermal excitations are integrably localized.
Norm, is that similar to 1D topological?
It is 1D topological.
No, sorry, 1D topological superconductor, and you store in the Majorana modes information. Can you map this model onto that?
No, I mean in the Majorana case, that's actually much closer to the Ising case. In that case, actually, well, let me see if I can answer your question succinctly. So in that case, in order to store a single quantum bit, you need to use both Majoranas on each edge. Here, it's a different.
Use just one edge.
It's a different topological phase. So in that case, actually, what ends up happening is the Majorana corresponds in the spin language to polarization in the z direction being stored, and it's kind of the strong zero mode of the Ising model, but it's not the same as this Haldane. Okay. But now, let's write down the remarkable feature. It turns out that the only thing we're going to do to modify the Hamiltonian is to put an I in all of these locations. And if each of these Ji, Hi, and Vi are chosen from sufficiently random distributions, not proved, but numerically explored quite extensively, chosen from sufficiently random distributions, aka now, unlike this case over here, which is undisordered, we're literally looking at the localized or disordered model of the version of the exact same model, but we still want to have, on average, that the J's are larger than the H's and the V's. Okay? That's also true in that case as well. It turns out in this case, if one many-body localizes, it turns out that one can many-body localize all of the excitations over here. And now, even if we start in an infinite temperature state, so begin at T equals infinity, so the density matrix is proportional to the identity. So you have a chain, density is right, and you perform the following quench experiment. You encode, you measure the two edges, and you now encode information into the edges. So you have a state that's a strongly, the thermal state, it's as thermal, high temperatures you can get, and now you measure the two edges, the two edge modes, and you encode information in them, but it can be quantum information in them. It turns out, because of localization, actually, again, each edge stores a quantum bit, but unlike the case over there without disorder where the temperature had to be effectively 0 or below the gap, here temperature can be arbitrarily large. And this has been shown numerically but hasn't been proven. So let's draw a little table for ourselves in the context of this, model. So at T equals 0, in the absence of disorder, on the edge we have a quantum bit, and in the bulk, we have no bit. At finite temperatures, in the undisordered case, so this is no disorder, or no MBL. At temperatures greater than 0, of course that's that over there, there's no bit on the edge, and there's also no bit in the bulk. What do we mean when we say many-body localization protected order? In the model that now has disorder, where I claim that it is consistent with many-body localization, at any temperature, or in particular temperatures above 0, it turns out you have a quantum bit on the edge, but actually in the bulk, you don't have no bit, it turns out there's disorder in the bulk as well, so actually you have a classical bit in the bulk. But really, when we speak about many-body localization protected order in this context, it's really referring to this case compared to the non-disordered case, where you have, at finite temperature, you have no bit that's stored on the edge. I think that's reasonable. Within 30 minutes, I would say. Okay, so that's an example of how many-body localization can allow us to see typically what we would imagine. I mean, for those of you who have learned this type of physics, we typically think about topological or SPT order at least as being a ground state phenomenon. That means we have to have temperatures below some gap scale on the problem. And what I mean when people mean when they say many-body localization protected order is precisely the fact that when one adds strong disorder to a problem, that it's possible that the order which we previously saw was restricted to the ground state is now surviving to finite energy densities. All right, thanks a lot. Should we say, well, maybe we
have now, let's say, about 2.5 hours time for questions.
Lovely, lovely, lovely. Yeah, please.
Actually, if any of the students have one, they can go first.
Yeah, or we can talk also during the... Yeah, please.
So how does this argument apply to other, for example, 1D SPT phase, like SSH model or spin 1 Haldane model?
Yeah, so this is kind of the analog of the Haldane model. I think, let me think if this is true. Dima, correct me if I'm wrong. Is it true that basically all SPT orders, all bosonic SPT orders are localizable? I think that's right? Yeah, so basically anything, so okay, maybe let me answer your question. You can ask yourself, I'm talking about protecting order. And the question you're asking basically is how general is your state of norm? Let me say that I find an interesting ground state. Does that mean that I can find a many-body localized version of this that survives the finite energy density? The answer is no. So in the context of these symmetry-protected topological phases, I think it's known that you can have, all of these are many-body localizable, so there are localized versions of this order that live to finite energy density, or in principle can, depending on whether or not MBL is stable in higher dimensions or not, or at least the time scales will be sufficiently long. There are no-go theorems, for example, that are inconsistent with many-body localization of certain types of order. So if you remember, Dima wrote out the kind of universal many-body localized Hamiltonian, this phenomenological model in terms of taus. It turns out that if your ground state of the system that you have has some non-zero thermal Hall conductance, you can show that that Hamiltonian cannot be massaged into the L bit, into the universal phenomenological Hamiltonian Dima wrote. So we, in that case, think that there's a no-go theorem at some general level for not being able to localize that specific type of order. But I think it's an open question in terms of fully classifying what types of order can and can't be localized. Is that right, Dima?
I think so. So I think what was the kind of symmetry that you have? So if you have an immediate symmetry,
yeah, right,
things get more complicated. So people, if you have, for example, a C2 symmetry, right, that also forbids localization in the sense that we discussed so far.
Max?
So even in the case where you can't protect at infinite temperature, all the eigenspaces are still 4-fold degenerate because like the Hamiltonian still has that symmetry. So is it a statement that like the degeneracy isn't due to an approximate factorization of the eigenstates into like bulk tensor with edge?
Yeah, okay, so I think it's a, right. So that exists, that degeneracy exists, but I guess the statement is, no, I think the loss of information is not due to that, it's due to the fact that basically, once you have excitations that are basically extended in the system, there's a leading order process where it turns out, like you would think about the scattering diagram, is basically your edge mode scatters with this extended bulk mode, but the extended bulk mode actually has basically weight on both sides of the chain, so it can then scatter with the other edge mode. And that scattering process is what loses the quantum information. So it's really, and now, you know, the way localization works, yeah, that's super important actually, I'm glad you asked that. The way localization works is that it localizes all of these bulk excitations. So actually what happens now is that if you want to scatter the information out of this, you have to scatter through these localized moments, which go higher order and get suppressed as e to the minus L over the localization length. Yeah, good question. Okay. Sounds like everyone's exhausted. Thanks for staying. Or
No. Let me ask one question.
Yeah, go ahead.
So, would these things be maybe more powerful for quantum information processing than the Majorana box?
Not really, I would say.
Okay. Because
I mean,
at least here you can go to infinite temperature, which...
Yeah, okay, so in some senses it's better, you know, what it doesn't have, of course, is that all of the information is somehow stored locally. So if you imagine coupling to a bath, and you have a noise spectral density that locally hits you over here, that can decohere your information.
And it's different from Majorana.
And it's different from Majorana, but of course, you do have the property that, at least in this localized limit over here, that it should be possible to see this at higher energy densities. But you don't have that non-locality.
All right, let's think. Mom again.